Welcome back, students. Lesson 21, Video B. This is the third to the last lesson. So congratulations for making it this far. Let's do a two-sample t-test independent samples problem. Example. You might ask yourself this question here: does college provide students with a beneficial education? Lots of people are asking this question out in the industry. Important skills such as critical thinking and reading comprehension are measured by a test. And there's two tests. At community colleges, it's the CCLA, it's the Community College Learning Assessment. At four-year schools, it's dropped to community, it's just CLA, College Learning Assessment. So here's what happens in this test. Independent groups of students take the test. A group of incoming first-time, full-time students, so true freshmen. We'll take a random sample of freshmen. We'll give them that test, the CCLA. And the second group, independent of the first, a group of graduating students, so students who are completing their degrees. We'll give them the test. It's not the same students. I agree, you could run this in a different way. Take the freshmen, and then as they graduate, give the same students the test when they graduate. That is not what's happening here. We've got two independent samples. The idea behind the test is quite simple. If college provides a worthwhile education, then the graduates ought to do better, right? They've been in college for, earning their associate's degree at the community college level. Graduates ought to have a higher mean score on the test. So in this example, we're going to test that out. I found some data on the internet. Just did a quick Google search for community colleges, CCLA, and Howard Community College came up. And it's a little bit dated. It's from fall of 07 into spring of 08. The results are listed below. This was for one portion of the test, the analytic writing tasks. Okay, so first year students, we had 65 of them. Their average score was 1026. And their standard deviation was 158. Graduates, exiting students, 66 of them took the test. Their average score was 1101, standard deviation of 133. And so now we're going to run the test. Are you convinced, based on this small sample? Now clearly at Howard, there's more than 65 incoming students. This is just a small sample. And clearly at Howard Community College, there's more than 66 graduates. Using the sample data, are you convinced that the graduates do better on this test overall, on average? Okay, so that's the thing. Probably, let's label these numbers here. I'm going to put, I know this is on the bottom row, but I'm going to call this my first sample. And I'm going to call this my second sample, and here's the reason why. I'm noticing that the graduates have a higher mean score. I would like to, when I do my subtraction for the difference, I always like to try to put the bigger one first, so that when I subtract I get a positive number, and then I can run the test as a greater than test. It makes more sense to me, right? Do I have evidence that the graduates do better or have a greater score on average? So I'm going to call this my first sample. Put the symbols in. We're brand new at this. This 66 would then be my N1, sample size 1. This 1101 would be my Y bar 1, right? That's my first sample mean. And this 133 would be my S1, my standard deviation from sample 1. And then the top row here, this would be N2 is 65, Y bar 2, 1026, and S2, 158. Okay, so we can handle that, just the first sample's in the bottom row. You could reverse these and then you would run a less than test. I find those more difficult to comprehend, so I always try to force them into greater than tests. We're going to go through the steps one at a time. If you go all the way back to the beginning of hypothesis testing, we laid out sort of a framework to run these problems, and so we're going to go through step by step. First thing, you've got to read and understand the context of the problem. Right? Determine if the variable is categorical or quantitative. It's a test score. It's quantitative, right? It's numerical. And of course, if it's quantitative, we're working with means. We're in the two sample chapter, but think about it. I've got two samples, right? Incoming students, graduate students. So graduating students. So this is a two sample mean problem. It's a two sample t-test. And finally, it's independent samples. All right, so we understand all that. We're going to run a two sample t-test. That's the official name of the hypothesis test that we're going to run, and we're thinking about the problem. We're understanding it before we start doing things. Parts 2 and 3, write down the hypotheses, check the appropriate conditions before proceeding. All right, so hypotheses. H sub 0, H sub A. What are we trying to show? Do we have evidence that the graduating students do better on average? So, mu for the grads, exceeding, this is the alternative, exceeding mu for the freshmen, the incomers, first years. It's just a subscript down here, right? Label them so you remember which one is which. And I'm purposefully putting graduates on the left and doing a greater than test. We'll always assume equality up in the null. So mu for the grads equals mu for the first years. We're looking for evidence that the grads do better. We start by assuming that both groups do equally as well on this exam. Check the conditions. Let's think what we need. Have to presume. Presume what? Both samples unbiased. In other words, we didn't take the 66 smartest students and use them as our sample for the graduates. Clearly that would bias the results and we wouldn't be able to conclude anything about the CCLA test. We can't presume that our incomers are our worst students or the honors class. They have to be unbiased samples. Okay. What else do we need to presume? Let's think about this. N1 was 66, N2 was 65. Both exceed 30. So we're working with the quantitative variable. Both exceed 30. We're covered there. It's helpful to graph. Now we don't have the data here, but I would always be graphing the data just to see what it looks like anyhow before I run and do that test. Presume there's got to be 660 students graduating, maybe. I don't know the school sizes, but we'll presume that both samples less than 10% of their populations. If there's one condition I kind of sweep under the carpet, it's this 10% condition. I probably shouldn't say that on video, but in my opinion, more data is always better than less data. So I will just be willing to presume that those are less than their respective class sizes. And I'm also under the assumption that, look, there's more students always coming to these schools. And the reason we check that's for independence, and I'm not terribly concerned about that independence condition not being met. All right, let me take a peek at my notes here. I guess you're on the back page, right? Variables quantitative, I'll write that down just for completeness here. We're running a test for means, and so the very first or last thing we should be thinking about, the variable is quantitative. We covered that already, but I guess I'll write it down for permanent on the internet here. All right, looks like we're good to go with the conditions. We can run this test. Part 4, based on the collected sample data, convert your data to the test statistic. And remember in this note packet, you're given the degrees of freedom because the formula is complicated. In class, we'll run these tests directly on StatCrunch and you'll see where that number is coming from. Okay, but just trust us, it's 124.699 for this problem. All right, make some space here. Part 4. Okay. Test statistic is a T. It's y bar 1 minus y bar 2. It's divided by the standard error of the difference, which is S1 squared over N1 plus S2 squared over N2, whole thing square rooted there. Okay, so the numbers are on the front page in that chart, and so I'm just going to plug them in here. Remember, we called our graduates the first sample, and so I'll take the 1101. That was the average from the graduates. I subtract off the 1026. That's the average from the first-time students. Divided by big square root. S1 squared, so this would be the 133 squared over the sample size 66. Plus, for the other group, 158 squared over 65. A little bit of a mess. Make sure that you get the difference on top divided by the square root of this mess here, the 133 squared over 66 plus. Okay, pause the video, see what you get. I'll tell you what you should get. If you do this, looks like about 2.937. That's the test statistic. That's a T. We don't want to lose sight. What on earth does this number mean? Like, formulas are getting complicated. We've boiled it down to 2.937. What does that mean? Let me tell you. What's the difference? If I look at the 1101 minus the 1026, subtract these off, isn't this a 75-point difference? So from our two samples, the graduates did 75 points better on average than the freshmen or the incomers. What are we testing? We're testing for no difference. So here's what that test statistic means. Our 75-point difference is about 2.9 standard errors above 0. Right? We're presuming no difference. So I'll put a little summary here, because I don't want to lose sight of what this number means. Our 75-point difference is roughly 2.9 standard errors above a 0 difference. Okay? We're presuming no difference. We had a 75-point difference. Are those two sample means, are they far enough apart to convince you the graduates do better on average? Right? Is it too close to call? Are they way out here? That difference is that many standard errors, about 2.937. And in my head, I know we're working with T's, but that's almost 3, and we sort of know that 3 standard errors is usually pretty unusual. Okay, so I'm thinking we're rejecting the null, but we do have to get that p-value. All right, pause the video if you don't have everything that you need. I'm going to flip to number 5 here. Determine the p-value. You can't lose sight, students, of the big picture. I know that the problems are getting a little bit more complicated, but determine the p-value. I draw my t-model. Here's a t-curve. Degrees of freedom would be provided by technology, and technology tells us it's 124.699. T-curve is centered at 0. I'm going to put my test statistic on the model. And what did we get? We got a 2.937 that's pretty far up here. Here's my 2.937. And if I shaded this, that is the p-value. Of course, to get that, I would use the StatCrunch T calculator. We've done enough of them, I've got to presume as college students you could go to StatCrunch and just get this number. right? I shade up, I put the degrees of freedom in, I go up, and I'll get that p-value. It's got to be small. What is it? Oh, 0.002. 0.002. Now, nowhere in this problem, I believe, does it say, oh, run the test at 0.05, 0.01, point whatever, and it doesn't. Even if it did, this p-value is in the overwhelming evidence department for the alternative, so the data is convincing me what? The data is convincing me that on average, graduates do better on this analytic writing portion of the CCLA, which is good, right? I guess after you've been in college for a few years, you should do better on this test, on average. 6 and 7, if the p-value is small, which it is, you'll reject the null in favor of the alternative. Part 7, write a concluding remark in the context of the problem. And I guess there's one last question at the end, which we'll handle when we get there. If the p-value is small, reject the null. This is clear-cut, reject the null. Without a doubt, don't think, don't blink. 0.002 is below 1%, reject the null. Write a concluding remark in the context of the problem. There is, oh, I'll even say overwhelming. There's overwhelming evidence that grads, on average, that, oh, it's got to be in there on average. I'm comparing means. Certainly there are some freshmen that would do better than some grads, right? But we're comparing averages. This has got to be in there somewhere. There's overwhelming evidence that grads, on average, outperform freshmen on this portion of the CCLA at, oh, what was the school? Howard, Harvard, Howard, yes, the Howard Community. There. Oh, HCC, Howard Community College. There's overwhelming evidence that the grads on average outperform freshmen on this part of that test. Okay? So I'm sure everybody's happy about that, faculty, administrators, students, right? It seems like maybe there's a worthwhile cost and time for going to this school. Okay, there's one part at the bottom. Final question, if we made an error, what type of error did we make? What are the chances we made that error? And explain what this means in the context of the problem. Here's what you ask yourself. Self, did I reject or fail to reject? We rejected. Since we rejected, could have made type 1. Since we rejected HO, could have made type 1 error. Emphasis on could. Don't get me wrong, this isn't a coin flip. A 50-50 chance I made a mistake or not. Could have made type 1 error. What's the chances? Once we reject, the chances are the p-value. Probability that we made a type 1 error in this case is exactly the p-value, which is exactly 0.002. This is 2 in 10, 100, this is a 2 in 1,000 chance. 2 in 1,000. I'm no mathematologist, that's about 1 in 500. Right? So there's a 1 in 500, it's a coin flip, but it's a weighted coin, right? There's a 1 in 500 chance we're making a type 1 error. I can sleep at night with those odds. What does that mean? So if we did, if we got really unlucky data, I mean 1 in 500 chance unlucky data. If we did make this mistake, what does it mean? It means grads are, on average, no better on this test than freshmen. It's a tiny chance that this is what's happening in reality. The data is overwhelmingly pointing to that grads do better on average. But there's a 1 in 500 chance that if we did make that mistake, grads are on average just no better than freshmen. This had some weird data. Or some biased data. Who knows? Maybe we hand-selected the best and brightest graduates just to sound good. I'm not saying that happened. But you've always got to think about these what-if possibilities. All right, so nice little problem here. We're down to just 2 videos. Kim's going to come back, support these hypothesis tests with a confidence interval for the difference, and we are going to wrap up this course. So thank you for watching, and we will see you in class.